If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay students, I welcome you all to lecture 33 of this switchgear protection series. So till now we have studied the idea of the differential protection scheme and the percentage bias differential protection scheme. So it's time to implement that idea. So for that we start the topic, that is transformer protection. So we'll start the topic with some brief discussion about transformer, not operating principle, nothing sort of that, in the protection perspective. Then we will go to different protection schemes in transformers that we generally apply. So depending on the voltage rating, current rating and the importance of applications, your different types of transformer has its different protection scheme. Because in transformer we have distribution transformer, we have power transformers. So different sorts of transformers are there. So their protection schemes are also different. For less costly items, we will go for simple protection schemes. And though the transformer which are very costly, that are the power transformers, we will go for elaborate study, all different types of protection philosophy we will to put. The idea is simply economical, because if you put everything in a small transformer, every protection, then the cost of the protection will be more than the transformer itself. So there is no utilization of that. You are purchasing a locker which is more costlier than the item you are putting it. So it is less economic. There is no requirement of that types of protection scheme which are costlier than the equipment itself. So that's why a distribution transformer may have only overcurrent protection. You will see in distribution transformers mainly overcurrent protection, or you can also see there are fuses are connected just to fuses. Also you can think of overcurrent protection type. And power transformers, you have different types of elaborate protection schemes. There are different protection schemes we will be using in a power transformers, not a single one. Different types of relay we will see. So in three-phase transformers that are normally used, so we have different types of format. We can use a single phase 3 transformer for each phase, but the normal practice is to use a single transformer with 3 pairs of winding around a common magnetic core. One magnetic core we will put in the limbs all the 3 windings, the 3 limbs. Okay, what are the different types of faults then we encounter in a 3-phase transformer? So let us go through different types of faults, then we will see which protections we are skin, or how, for which type of fault, what type of protection schemes we are using. The common faults which are used in transformers, inside the transformer, is winding to core fault. That means you have a core and you have windings around it. So that winding got shorted with the core, because with the core you will put some laminations, and after that each coil is laminated, the wire itself is the laminated wire, and there will be laminated sheet between these two, some sort of insulations between that core and the wire will be there. That insulation has failed, and due to which these winding touched the core, so a phase to ground fault occurred. So that is the winding to ground fault, which is common in transformer. Phase faults, that is interconnection between phase A and phase B inside the transformer, is very rare, because they are in different limbs. This is phase A limb, this is phase B. It is very rare that some winding is gone out of this and then it come in contact with this. So these are far away. So these are not so common inside the transformer, but at the terminal they are common. Means at the output terminal you have a transformer, then you have output terminal, phase A, phase B. So here something may fall and these two can get shorted. So that's possible outside, that is in the terminal. For large oil filled transformer, oil leakage leads to fault. If the oil level is falling very low, then transformer will get heat up. That will make your winding more heating up, then winding can burn. So that will leads to a fault. So we have to think of that, think for that also. Now one phenomena that occurs in switching of an unloaded transformer, we will have a high magnetic inrush current, because if it is not loaded, the initial current transformer will take will be very high inrush current, we say, which is 6 to 7 times or 7 to 8 times your normal fault current, but it is not a fault. You have to take care of this one also, so that in case of unloaded transformer again turned on, system should not treat it as a fault. It should separate it. So how we will separate it, we will see. We will using harmonic restraint coil. So we will see that one. And interturn faults means, suppose there is a winding and you have, how many windings are there? 1, 2, 3, 4. Say 4 windings are there. So it was supposed to go through the 1, 2, 3, 4 winding. But interturn, that means this and this get shorted. So how many turns will be now? So 1 turn, 2 turn and 3 turn. So 1 turn is bypass. So current is not flowing through this. So current will come through this, sorry, not this one. So suppose there are 4 coils. Suppose these and these get shorted. So no current will flow through this. So current will come through this, then it will pass through this, and then it will. So now current will pass through 3 winding. So your effective impedance get reduced, but it will not take as a high as fall current. It will take higher currents, but not as fall current. So these are known as interturn faults. So due to this, large fall currents will not come, but gradually as the currents is increased from normal what is scheduled to flow through this coil, it is increased a little bit. So hot spots will be created on the windings. Hot spots means you will find this dot 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 because of constant overcurrent, small amount of overcurrent, but it is constantly flowing through it. So small hot spots will be there, and eventually the degradation will occur, and after sometimes it will fail. So its life will get reduced. So you have to take care of that also. And one thing is overfluxing. Overfluxing that can be happen to due to under frequency, due to some conditions in the system frequency falls below, or due to certain over voltage also. Overfluxing can happen. Overfluxing will lead to magnetic coal saturation, which will lead to your temperature rise, different types of so it will be as deadly as your overloading condition. So it is fatal for fully loaded transformer. So you have to take care of that overfluxing also, so that it should not be happening. So these are different types of faults. So if we'll start with the very basic fault, basic operation, basic protection, that is overcurrent protection in a 3-phase transformer. You can have a transformer which is a star grounded primary and a delta. So overcurrent protection means you will put, you have already seen overcurrent protections. I think in lecture 15 we have seen 2 overcurrent. You can go through that one. I will provide a link. Here we are putting 2 overcurrents and 1 earth fault relay. So I am not going to explain why 2 overcurrent, why not 3 overcurrent. We have discussed in length in that lecture. You can refer that lecture, or you can listen it one more time so that it get refreshed. So 2 overcurrent relay in 2 phase and 1 earth fault relay. So which will cater all the 11 types of faults that can occur after that, after this CT portion. So this is the basic protection scheme for the transformers, but it is very common. This is only for the primary protection for small transformer. It is for small transformer they are using, and it is a backup for large transformer, because for large transformer other sophisticated protection schemes will be coming. We will be dealing that one. So it also has a backup protection. If everything fails, then this will occur. So what is the plug settings of the phase relays? We have discussed in that lecture also. The plug setting, it should be, it's like overcurrent relay or IDMT relay, you can say. It should not pick up for maximum overload, so that it can distinguish what is the maximum overload and what is the smallest fault current. It should operate for smallest fault current, but it should not operate for maximum overload. So your plug setting should be in between maximum overload. This is maximum overload, and it should be in between, and minimum fault current. So it should somewhere in between that. So that for this it will not trip, but for this it will trip. So your plug setting should be in between these two. Then what is the plug setting for the ground relay? Ground relay is independent of what is the load. It is not depending. The phase relay is depending on load, because you are thinking how much overload it will, how much current will flow through the phase. But normally with the ground relay, in ideal condition there should be 0 current. But always system there will be something imbalance will be there. So imbalance current will flow through the neutral or ground relay, because due to system imbalance. So it depends on how much imbalance you are allowing in the system. There are some standards, you can allow 5%, 10% imbalance. So there are IEEE standards, what is acceptable for your system. So you will set that as a plug setting. Anything above that imbalance occurs in the system, it will treat as a fault. Okay, that's all for overcurrent relay, and that's all for today. So next we will implement a differential protection relay, differential protection scheme in the transformer. If you like the video, then press the like button, and please give your valuable comments in the comment section.